Okay, so in this video, I want to talk about how we get the equation of a plane. How does this make sense geometrically? Because in the notes, the equation of a plane is just kind of given to you, and I want to explain why this works. So I will say that the equation of a plane is similar to determining if 4 points are coplanar. Okay, and so what does this mean? Okay, so let's say I have my three-dimensional system here, three-dimensional space, and I've got the point P over here. Okay, I've got the point Q over here, got the point A, and maybe another one, B. Okay, well I can make 3 vectors in between those 3 points. Okay, so the 3 vectors would be PQ, one vector right there, PB, vector in the middle, and PA. So there are kind of 2 ways of thinking about how to prove if those 3 vectors are in the same plane. Okay, and that would mean, if they're all in the same plane, that the points that make them up are coplanar. So we could think about if we take those 3 vectors and try to make a parallelepiped like we did in the last video, if the volume of the parallelepiped they form is 0, well that would mean that it was flat like a pancake, literally squished. So that could mean that they were all coplanar. Okay, so the parallelepiped, goodness, is flat. Okay, which means the 3 vectors and points are coplanar. Okay? Or another option, if you like to think about it this way, is you could find a vector normal to the plane by choosing 2 of the vectors and taking their cross product. Okay, so you could find a vector normal or orthogonal to that plane. So by finding, let's say PQ cross PB, okay? And remember, PQ cross PB is perpendicular to this one and this one, both of whom we will assume are in the same plane, okay? Then we could test if the vector PA is also perpendicular to this vector. Because if this one is also perpendicular, then it must be in the same plane as these 2 separately. Okay, so we could do that. And let's say that we found the vector PQ cross PB, and we called it some normal vector N. Okay, then if we wanted to test if N and PA were orthogonal or perpendicular, okay, we could take their dot product. Because remember, if the dot product of 2 vectors is 0, then they are perpendicular. Remember, that comes from that formula with cosine of theta, cosine of 90 degrees is 0. So if I dot N with PA and get 0, then I will know that they are perpendicular. Okay, so if N is an orthogonal, because these are vectors, to PA. Okay, but if we substitute our definition for N into this formula, I get that PQ cross PB dotted with PA should be equal to 0, which is the exact same thing. This is the scalar triple product, or the formula for the volume of a parallelepiped. So we're basically saying the same thing here as we are here. Neither of them is any better than the other. We end up doing the same kind of formula. Okay, so I want you to remember this formula as how we could make the equation of a plane. Okay, and I am going to give you an example because it seems like this would be useless if we knew all of the coordinates of the point. Okay, or we would just be testing to see if those 4 points are coplanar. What if we want to write the equation of a plane? Okay, well then let me give you an example. To write the equation of a plane, the notes will tell you that you need a normal vector and a point that's already in the plane. And let me show you how that works. Okay, so if I want to say find a plane, let's say the equation of a plane that goes through the following points: 3, -3, 2, 1, 0, 1, and 1, 1, 0. Okay, so that's 3 points. Now remember, 3 points can only give us 2 vectors, but I'm going to claim that's all we need to write the equation of this plane. First, we want to find, that's a 1. Find those vectors. And I'll call one of them A. Let's make A go from this point to this point. So remember to think about the change. Okay, I would get -2, 3, -1. And vector B, let's make B go from this point to this point instead. Doesn't really matter, whichever you would like. It shouldn't matter. Okay, so again, let's get -2, this time 4, -2. Okay, great, so those are the vectors that make up, are already in the plane. Okay, and I'm gonna go with the second method we talked about earlier. So let me pull that down again. Second method. Okay, I'm gonna find a normal vector, and then I'm gonna create a new vector in the plane. Let's call it PA, or yeah, it was PA. Another vector in the plane, and dot them together to get 0. Okay, so first I gotta find the normal vector. And remember, if they do equal 0, that means that everything is coplanar. Okay, so first I gotta find the normal vector. We find the normal vector by taking the cross product of A and B. And I do want the vector, I don't want the magnitude this time. Okay, so remember that that is the determinant of I, J, K, and then -2, 3, -1, -2, 4, -2. Okay, this will be equal to I, okay, times the determinant of 3, -1, 4, -2, minus J times the determinant of -2, -1, -2, -2, plus K, and the determinant of -2, 3, -2, 4. Okay, now let's set about computing these. So that's I times -6 plus 4, -J times 4 minus 2, there's a lot of negatives in there, plus K times -8 plus 6. So actually this vector is -2I, -2J, -2K. So you could also write this normal vector, okay, as -2, -2, -2. Okay, so again, recap. We've got 2 vectors, A and B, that are in the plane already. Now we have a normal vector that is orthogonal to the plane. In step 3, I am going to make a new vector between one of the points, okay? And let's choose, I don't know, I guess this one seems the most simple to me, but you could choose a different one. And an unknown point, X, Y, z. And I'll explain why I want to do an unknown point in a minute. Okay? Let me scoot this up a little bit. Okay, now I want to make this new vector, and this new vector will be, think about the change. So we'll go from this point to this point, so x minus 1, y minus 0, z minus 1. This is our new vector. Now to determine if this vector is also in the plane, we need to dot this vector with this vector and set it equal to 0. So we're going to dot -2, -2, -2 with, oops, excuse me, that's a dot, x minus 1, I'll simplify it to y, and z minus 1. And this should be 0 if this is orthogonal to this. And remember again, if this is orthogonal to this, this will be in the plane. Okay, so if we dot them, we'll get -2 times x minus 1, minus 2 times y, minus 2 times z minus 1 equals 0. Okay? And you're like, Miss Kelly, I feel like we didn't solve anything. But what we did is we created an equation that gave us the conditions for any point x, y, z that will be in this plane. Okay? Because if the point x, y, z satisfies this equation, then it's definitely in the plane with these other 3 points. So we kind of artificially created some conditions to test points that would satisfy this. Okay? And we know that there are going to be a whole set of points that will satisfy this, but a whole set of points that won't. And so this is actually the equation, okay, of the plane. Any point that satisfies this equation is in the plane with these other 3 points. Okay? And you're thinking, okay, so how does this relate to some of the formulas I see in the notes? Well, this is the same formula as a x minus x naught plus b y minus y naught plus c z minus z naught equals 0, where a, b, and c are components of the normal vector. And I'll call that normal vector just like n for reference. Okay? A, b, and c are the components of the normal vector, and x naught, y naught, and z naught is some point that's already in the plane. You can also write this formula. If you wanted to multiply it out, you get -2x plus 2 minus 2y minus 2z plus 2. Okay, so that, equals 0. So you should get, well, here's the thing. We could divide everything by 2. Maybe that'll make it a little bit simpler. Let's divide everything by -2. I like all my variables to be positive. You could write it this way. You could divide it by 2. You could divide it by -2. I like to divide by -2. So x divided by -2 will be -1 plus y. This is supposed to be a z, isn't it? Oh, made an error. Good catch. Plus z minus 1 equals 0. So if we combine the like terms, x plus y plus z minus 2 equals 0. So this is another way to write the plane. Okay? All right, so one more to recap. To write the equation of a plane, what you can do is, if you're given 3 points, is make some vectors. Okay? Then find the vector that is orthogonal to this plane. Now that we know how this formula occurred, you can skip right to this step and plug in the components of the vectors and a point that's already in the plane and set it equal to 0. But if you forget why that occurred, we were testing whether or not these 2 vectors were in the same plane as this vector right here. And this vector gave us some, once we had tested that by dotting it with the vector that was orthogonal, we knew was orthogonal, okay? It gave us some conditions that a point x, y, z would have to fall into or obey in order to be in the same plane.